since we talked about heart rate since we have talked about heart rate and stroke volume in the last two videos, it only seems fitting to talk about cardiac output. So we've got our couple of objectives here. And so with this, all right, sorry, I was a little distracted there. Someone was coming to see me. Well, Devin told him to come see me during lab, and I wasn't sure if they were coming in or not. So our topic and outcomes are as follows. Pretty straightforward, basically how to calculate cardiac output, and then talk a little bit about something called ejection fraction and cardiac reserve. So cardiac output is just how much blood leaves your heart every minute. This is essentially measuring the flow of blood out of your heart. So it's measured in liters per minute, so volume per time. All right. And we calculate it by going heart rate times stroke volume. So how often your heart beats times how much comes out with every contraction or every beat. So if we've got this example here, end diastolic volume is 160 and systolic volume is 60. That would mean our stroke volume is 100. If our heart rate is 70 beats per minute, that means our cardiac output would be 70 beats per minute times 100 mils per beat. And so we get 7,000 milliliters per minute, but we would change that into 7 liters per minute because that's what we report cardiac output. So stroke volume we report in milliliters. Cardiac output we report in liters. So how does heart rate and stroke volume affect cardiac output? If we increase heart rate but keep stroke volume the same, that's going to increase cardiac output. If we increase stroke volume without changing heart rate, we're going to increase cardiac output. However, usually what happens is if we increase one, the other one will decrease just to maintain cardiac output. And this has to do a lot with filling time, which we talked about during the heart rate video. If I increase my heart rate, there's less filling time, and so there's going to be less blood generally to eject out of the heart, but not always. All right, so this leads to something called cardiac reserve. And so cardiac reserve is just what's your current cardiac output and what's your maximal cardiac output, okay? And so typical cardiac output is at rest is about 5 liters a minute. And like I talked about during the first day of class with the cardiovascular section, some people, a typical person has a cardiac output of 20 to 25 liters. And in some elite athletes, that can be 40. So if you went 40 minus 5, that would say that these elite athletes have a cardiac reserve of 35 liters a minute, which is tremendous. Okay, so if you have a high cardiac reserve, that's good. Low cardiac reserve, that's usually bad because that means something's going on. But obviously, you need to take into account what you're doing. If you're measuring cardiac output in the middle of some intense exercise, you're going to have a relatively low cardiac reserve. Then there's also this thing called ejection fraction. And so ejection fraction is just what percentage of your end diastolic volume is being ejected from the heart when it contracts. Okay, it's a percentage. So if we go back to this example, or go back to this one, or use this one, this is a different one. So our stroke volume here is 70. Well, to calculate ejection fraction, we take that 70, okay? So stroke volume, not end systolic volume, but you take stroke volume and you divide it by end diastolic volume, multiply it by 100 to get percentage. And so in this case, we'd get 50%, all right? So that's how you calculate ejection fraction. All right, so can you do the following two things? Can you calculate cardiac output? Can you calculate and describe ejection fraction and cardiac reserve?